right, so we're a match predictor. Next slide, please. So match predictor predicts the outcomes of the top 5 leagues soccer matches. So we're looking to make this project for soccer fans, analysts, and sports bettors. We thought this was an interesting project because soccer accounts for the largest volume of the sports betting industry, and it's something that's very unpredictable. For example, Leicester City defied 66,000 odds in 2016 to win the Premier League, and previous attempts at this problem weren't very successful, with only 50 to 55% accuracy. Next slide. Okay, so we were looking to collect team statistics data, so we're not looking at the player level right now. We had 64 different features to look at, including average goals, points per game, shots on target. And our label for each sample was just the result of the game: home team win, away team win, or tie. And we had 13,300 data samples to work with. Next slide.
So to choose our inputs from those 64 potential features that we could use, we used kernel density estimation graphs and box plots to determine like how different each of the features were in terms of predicting the outputs. So as you can see, this graph on the left is pretty nice because each of the outputs obviously have a different density for the inputs, and it's visibly obvious. And then on the right, you see a less good graph where the input feature doesn't really help us predict the outcome. So to account for the current team performance or the form, we would average stats over a certain given number of game weeks. And then also one issue we ran into when balancing the data set, you can see in this pie chart, is that home team wins accounts for most of the data set, so we had to balance that out. Next slide, please. Here you see the dissection of our sample inputs. So the first six indexes, 0 to 5, describe the home team characteristics. 6 to 11 describe the away team characteristics. And the final input is actually the label, not the input. Next slide, please. So at its core, our model is just a multi-layer perceptron, which is a great solution to this type of problem where you have a small input vector and you would like a classification output. Our output is 3 numbers, each representing basically a probability of a given outcome, either a home team win, an away team win, or a tie. And then you see the architecture modifications and hyperparameters we would change during our hyperparameter optimization, but those are quite standard, so we'll gloss over that. And then if you focus on that table in the bottom right, which is a bit too small, but you see some reference models we took from a research paper where they were also predicting sport game outcomes. And we found that the models that had 3 output neurons were the most accurate, as well as models that have 3 to 5 neurons were the most commonly used. Next slide, please. So using those reference models and also this rule of thumb given to us by Wei, we started off with our architecture choices with the above architecture choice at the top. And this actually surprisingly turned out to be the best architecture choice, even though we started with it. But it's extremely lucky, but it was also kind of expected because we based it off the reference models and also off this rule of thumb, which says the number of training examples that you have available to you should be at least the same order of magnitude as the total parameters in your model. And one big issue we kept running into in this project was that our model would overfit on the training data after about 20 to 40 epochs. And we tried reducing the capacity of the model to reduce this, but it didn't help. And then we tried implementing weight decay, which you can see on the next slide. So on the right, you see weight decay being implemented, and on the left, no weight decay. And when we implemented weight decay, it did stop the divergence between the performances, which allowed us to train over more epochs without overfitting. But in the end, we found our final performance was the same by just implementing early stopping on our model with no weight decay. Next slide, please.
So our model was able to reach a validation accuracy of 48.2% in 100 epochs and test accuracy of 47.3%. We decided that accuracy would be our only performance metric because in sports betting, the type of incorrect answer you get doesn't really matter. You still lose money. We believe this accuracy will be similar if our model is run on data from other leagues because their data set included 5 different leagues already. Next slide. So we had 2 different baselines, a random guess and an always guessing home. So we had to at least beat 45.5% for our model to be successful. We also wanted to be competitive with existing models that came from our reference papers. So within 48 to 55%, we were able to actually meet this goal using more leagues and less features, which was very impressive. That being said, there's still a lot of room for improvement compared to human predictions. Sports analysts are correct 60 to 65% of the time, with soccer analysts around 50 to 55% of the time. Next slide. So our model's performance justified the use of MLP to solve this problem. Expanding the data set demonstrated generalization, but hindered our model's accuracy as we had to deal with more uncertainty between our samples. For example, the Italian league is much more defensive compared to the English league, and that just made our accuracy a little bit lower. The small data set made overfitting a lot more of a problem than we anticipated. In the future, we'd look to optimize weight decay and include dropout. We'd also look to expand data set using player data and non-team independent data as well. I guess that's the end of our presentation.
Great. Thanks. You know, if you were able to succeed in any serious way, you'd be rich, right?
This is true.
Maybe this is not the first team in this 3 years of this course that's tried to do this, but maybe that's a thing I should say before people jump into this. Let me ask a quick question. One is, just the comparison of the accuracy. So if you predict home, what is the accuracy you get on the 3 classes is what, 45% or something? Just predicting home?
Just predicting home, yeah, you get 45.5%, but that's when we use, so if we completely used an unbalanced data set to validate on, we would get 45.5% if we just guessed home every time. But we were also validating on a balanced data set, like class balanced. So each class had the same number of samples. So if we were guessing on our validation set, we would have gotten 33.3.
I see. And you get 47 on that.
Yeah.
So that's the claim for success. I see. Right. I guess that takes you out of the you'd be rich question when you balance your data.
Yeah, so, a little bit.
Yeah, that's interesting. Who's Paul the octopus, by the way? He seems really good at this.
He was an octopus that sadly recently was sold to a sushi restaurant.
It's not a nickname, it's an actual octopus.
An actual octopus who in the World Cup, which actually in the World Cup there's only 2 outcomes, they don't allow draws, but he predicted 85.7% of the matches correctly.
I see. Wait, any questions?
Yeah, first of all, did you try batch norm? Usually I found that being most helpful for fully connecting layers.
Pardon?
Did you try batch normalization?
Yeah, we did a little bit. The results were pretty lackluster, other than it did train a bit more smoothly, but it wasn't worthy of being in the presentation. So, yeah.
And maybe perhaps analyze the games that the model failed to predict. Are those the matches that are like really upsets, or is just the model is not catching?
If we had more time, we would have definitely delved deeper into those analytics. But
so that's a great point. That it was a requirement of the presentation. I want to see this in the final reports. A qualitative result is what he's talking about. So you pull it up and you go, why was this one wrong? Maybe there's something, you're soccer fans, you can figure it out. You have to do something like that. Just to stop from just turning cranks. Like that's the danger in this course. You go, it's data, I turn cranks, I don't have to think about it. You're soccer fans, maybe you can figure out what went right or wrong, perhaps. It's tough on this one.
Yeah.
I meant to say I did like the early work you did on feature selection. That's making use of domain knowledge, and so that's good to see. I hope that's clear in the report as well. Sorry, I interrupted you. Wait, anything else?
No, it's good. It's good. And that's basically all. Good job, guys.
Thank you.
Any questions, comments, suggestions, applause from anyone else? Any soccer fans in the class? All right.
Oh wait, what features did Paul the Octopus get for this problem? Like, did he get any information presented to him, or did he
It was
just
pretty
like call
much
it?
just reward. I think it was just like the size of the fish, probably. That's how he was doing the
Um,
predictions.
all right.
I mean, there's a fish for Senegal and a fish for France kind of thing, and he had to
Yeah.
pick. I see. Octopus are really smart, actually. Not very long, but they're smart. Okay.